Hello everyone, my name is Michael Königsmann. I'm in technical marketing for Keysight Technologies Network and Data Center Group. Today I'm going to show you our solution for Coherent Terabit research, which is based on our lowest noise 110 up to 110 gigahertz OMA system and the industry's fastest arbitrary waveform generator. This allows you to test QAM even beyond 100 gigabaud. The products that are involved are our 8190 series of arbitrary waveform generators and the N4391D optical modulation analyzer family. The test solution behind me can be used to mimic a complete coherent transceiver. So you can use parts of it, the transmitter part of it, to mimic a golden transmitter to test your receiver. And you could use the OMA side as a golden receiver to test your transmitter design. Let's have a closer look at the setup. Essential part of my transmitter setup is the arbitrary waveform generator, the M8194A, 120 gigasample 4-channel AWG. The AWG is driven by the optical modulation generator software, which we specifically designed for coherent signal generation on the electrical side. It is organized in different tabs. Waveform tab gives me access to the waveform definition. I can select the waveform format. It could be a QAM 64, 8 QAM, 16 QAM signal, or user-defined. In my case, it is a QAM 64 gray-coded. I can select the data source for it. The data pattern is a PRVS with a PRVS 15. Finally, I shift the two polarizations by 220 bit to finally send it out to the generator. Before I do this, I have access to a constellation map on the lower right-hand side, which shows me the constellation map of the signal I'm generating. Not to forget the symbol rate that I can set in this part here. I'm quickly jumping into the pulse shaping, which can be accessed from here. So right now I'm sending out a raised cosine 0.2 filter alpha. In the corrections tab, I have access to frequency response compensation by S-parameter de-embedding. In this case, I'm using the S-parameters describing my modulator to correct for them. I also correct for the channel response of my arbitrary waveform generator, basically a factory calibration that is done for each channel individually to provide a flat frequency response at the front panel outputs. The section in the middle gives me access to skews and gain imbalance settings, or de-embedding if you wish. Here we can optimize the signal for use as a golden signal to test receivers, or to compensate for remaining skews in my transmitter setup due to cables or other components in the electrical signal path. The corresponding frequency response is down in the picture down here. It gives us the combination of channel response and S-parameter de-embedding. The final tab, the basic setup tab, allows me to select from different arbitrary waveform generators, and also allows me to select my channel mapping, which basically describes which arbitrary waveform generator channel corresponds to which optical component. So channel 1 is Xi, channel 2 represents XQ. You can change that according to your setup. In my case, it is as it is shown here. The lowest section here gives me access to the amplitudes of the 4 channels. I can select individual values. In my case here, all of them are of the same amplitude. When I'm satisfied with my settings, I go over to the right-hand side and press Send Data to Modules and Run to finally get the signal uploaded to my arbitrary waveform generator. The electrical INQ signals now leave the AWG into the optical multi-format transmitter, a modulator provided by the company ID Photonics. The carrier is generated with this 4-channel tunable laser source. The signal leaves the modulator on this yellow fiber Some signal conditioning is going on. I have a coupler, a filter, and an amplifier. They are used to amplify the signal in the case of the amplifier and get rid of some broadband noise in the case of the filter. Once the signal enters our optical modulation analyzer, we find the lower box here, which is containing a complete coherent receiver. So there is a local oscillator built inside that could also be used for external experiments. There is an optical hybrid built inside that converts the optical signals into optical I and Q. These optical I and Q signals finally enter the photodiodes on the internal end of this setup here and are converted from optical into electrical signals. The electrical signals finally enter the 4 channels of my oscilloscope, which is from the UXR-series of real-time oscilloscopes available with a bandwidth of up to 110 gigahertz. They run at 256 gigasamples per second with a vertical resolution of 10 bits. The signal that I'm generating can be analyzed here. I set up the measurement already. You see on the upper left the 2 constellations for the Quant 64 that I'm generating. Below that, I have the optical statistics of my signal. Here, we concentrate all the critical parameters of the signal, like error vector magnitude, Sundar rate, imbalance between the 2 polarizations, frequency error, skews between the channels, skews between I and Q inside the channels, and for those of you who are more familiar with the Q factor, also we report the Q factor. At the bottom here, we see the spectrum of the signal. On the right-hand side, we have optical properties. Here we show for each of the 2 polarizations the individual error vector magnitude readings, gain imbalance, offset, quadrature error, skews, and again the Q factor. Below these properties, we have what we call the adaptive equalizer. This is used to compensate for linear frequency response, phase and frequency response in the transmitter and in the transmitter part, so that we finally get to an optimized error vector or more optimized error vector magnitude reading. The 2 windows on the bottom right show bit error results. So I'm running a bit error measurement on my signal. You see the reported DER values here. We can estimate the DER from EVM readings. Also, we report how many bits we found in error, how many uncounted bits we had so far. And again, we see our polarization delay of 220 bits that I set on the transmitter part. That concludes the one panel tour and the overview on the Coherent Terabit research. Thank you for watching.